Hi, I'm Shanawaz. Last time we did covering space and covering maps. So let us recall what we did last time. So suppose we are given two spaces, say x and y, which are topological. And let us suppose we have a map P from this space x to y. Now we call this P a covering map and this x to be a covering space of y. If suppose this is space y and this is space x, so if for each point in y, so first of all P should be surjective, and second that if we take any point, say y in this big Y, so there must exist a neighborhood of y, that is we have an open cover of y. So if for each point y in y we have an open set V which contains y, then for this open set V it is in inverse image under P. This inverse image must be the disjoint union of open sets, say ui, where this I is in I. So this inverse image of V must be the disjoint union of open sets in X. So these UIs are open sets in X, with the property that this P, when we restrict this P to these UIs, so this must be a homeomorphism, that is it maps this UI homeomorphically onto V. Then this P is said to be a covering. And in last lecture we see that if we have any 2 points, say y1 and y2 in y, then the size of sets P inverse y1 and P inverse y2, this is always same. Now let us define the degree of a covering map. So we have a definition. So let us consider a covering from a space x to y. Let P from x to y be a covering. Note that these x and y, they are spaces, topological spaces I mean. So be a covering. So this is a covering of, suppose this y is path connected, so this is a covering of a path connected space. So this is the first item of the definition. Then we define the degree denoted by x colon y. So this is the degree of P. So this is defined as the cardinality of this set P inverse y for some y in y, for some y in y, i.e. this degree is defined to be the size of this set for any y in y. Note that this degree is well defined because of this reason, because for any 2 points, distinct points in y, say y1 and y2 in y, the inverse image of these pointers as sets, they have same size. So this is a well defined notion here. Now we have second item. So now if this degree, this degree can be finite as well as infinite. Suppose if this degree is a finite number, say n, in that case this p is said to be an n-fold covering. Otherwise p is an infinite covering. So if the degree of p is, if the degree is a finite number, say n, then we say p is an n-fold covering. Otherwise we say p is infinite covering. Now let us do an example of an n-fold covering. So this is the example. So let us consider x to be equal to y to be the unit circle S1, where this S1, it contains all those complex numbers with unit modulus, so this is 1, and let P be a map from, say, S1 to S1, defined as, so this P takes this complex number to its nth power, where this n is some natural number. So we claim this, indeed this is a covering. Now we claim that this P, this is an n-fold covering. Now let us see what happens here. So if we have a circle here, let us make it a little bigger. So suppose this is our circle here, so this is S1, this is S1, and this is our map P, which takes this Z to Z power n. So this is map P. Suppose we have a point, say Z here. Now this point Z is mapped to, so this Z is mapped to, now if Z lies on the unit circle, that is if mod of Z is equal to 1, then mod of Z to the power n is also equal to 1. So the image of Z under this map P, where P is defined like this, so this is mapped to a point which also lies on the unit circle. So this is some point, suppose say here this is point W, which is equal to P of Z. Now what happens here actually, so if we rotate this point from in anti-clockwise direction, this W also moves around this circle in anti-clockwise direction, but with a speed n times bigger than this. That is, if this Z is allowed to move around this circle once, this W, it moves around this circle n times. So suppose this n is equal to 3, what would happen? So if this z is mapped to z cube. Now what happens actually here? So let us uh, divide the circumference into three subparts. So this is one subpart here, so let us draw this again. This is one subpart. So from here to here, this is another, and from here to here, now suppose this z moves from, so these three arcs, they have same lengths, so we have divided this circumference into three arcs of same length. So if this z is allowed to move around this red arc, this w takes a full revolution around the circle. Similarly, if this z is allowed to move from here to here, once this w takes another revolution. And finally, if this z is allowed to move along this green arc once from here to here, this takes another revolution. So that means once this z takes a full revolution, this w takes three revolutions here. Now what happens actually here? So suppose this is some point y here, and this is the neighborhood of y. Now if we are looking the inverse image, suppose this is the neighborhood v of y. Now if we are looking to this set P inverse V, it is inverse image consists of three disjoint open sets. Now this P, this V has so it is inverse image lies here, suppose in this open subset, in this open subset, and in this open subset, because once we move this z along this red segment, it takes a full revolution. That means this segment over here, this has some pre-image here, because this P is given to be a surjective, because during this span on the red line, this takes a full round around this circle. So this segment must have a pre-image in this red region. Now again, when we travel along this region, I mean along the blue region, this takes again a full revolution. So this open set also has a pre-image over here, and finally it has also a pre-image in this segment as well. Now what is the guarantee that these sets are open? Now P is given to be a covering, so P, when we restrict to P to these, suppose these are Wi's or Ui's, when we restrict P to T's Wi, so this is a map from Wi to this V. Now this is given to be a homeomorphism. Now if V is open set here, this Wi has to be open, because a homeomorphism maps open sets to open sets. I mean a homeomorphism is an open map. Now let us exhibit these open sets and this set in this example. So let us move to the next page. So indeed P is a covering. So P is a covering. So let us take a point. Let z equal this e power 2 pi I y. So this is definitely a complex number with unit modulus. So this is a point on the unit circle, say S1. So then the open set, say let us consider this open set V here, which contain all complex numbers on the unit circle, while this X is allowed to move in this open interval. So actually this is an open arc. So this is the circle here, this is the point Z here, and around this circle, around this Z, this is the open set V here. Now we claim that this open set, this has a desired property. I mean, it is inverse image consists of and disjoint open subsets of X. I mean the circle S1. This has desired property. So indeed we have so this P inverse V. So this is union of these open sets J running from 1 to n. So this is e power 2 pi I x, where this x lies in the interval, open interval 1 over n y minus 1 by 4 plus j over n, and 1 over n y plus 1 over 4 plus j over n. That is, this is the union of these open intervals j runs from 1 to n uj's, where this uj, this is the open interval 1 over n y minus 1 by 4 plus j over n, and 1 over n y plus 1 by 4 plus j over n. So this is the open interval. So one can notice here that, so note that when we restrict to this P to uj, so this is the map from uj to V. So this is a homeomorphism. So this is a homeomorphism. So this shows that this P is an n-fold covering. Hence, P is an n-fold covering. Now let us do a lemma here. So let P from X to Y be a covering of a topological space then the map P is an open map. Now what do we mean by open map? An open map is a map which takes open sets to open sets. I mean, which carries open sets to open sets. So this is the open map. So let us prove this. So let P from X to Y be a covering. Let us consider any open set. Let U be an open set in X, be an open set subset of X. Now we have to prove that this P carries out this U to an open set. I mean, we have to prove this P of U, this is an open subset of Y. So we need to prove P of U is an open subset of Y. Now to prove this P of U is an open subset, so it suffices to prove that if we choose any element, say Y in P of U, then for this little y in P of U there must exist an open neighborhood, say V, such that this Y is in this V and this V is a subset of P of U. So it suffices to show that for each Y in P of U, for each Y in P of U, there exists an open neighborhood, say V, such that this little y is in V and this V is a subset of P of U. So this is what we had to prove here. So this must be true for each y in this set here, P of U. Now it is given that this P is covering. Since P is a covering, so P is a covering, then for each y in Y there exists an open neighborhood, say W, such that P inverse W is a union of disjoint open subsets. So since P is a covering, then for Y in Y there exists an open neighborhood. So this is by definition of a covering, say W of Y, such that P inverse W, this is disjoint union of say open subset is Wi, where this Wi, I in I are disjoint open subsets of X with the property that this P carries out each Wi on W homeomorphically with the property that this P, when we restrict this P on W, this carries out this Wi to W homeomorphically. So this is a homeomorphism. So this is by definition of a covering. Now also P is surjective because of the reason that P is covering. Also P is surjective. Therefore for this Y in Y, so therefore for this Y which we took from PU, there exists some X in U such that P of X is Y. Now also this Y is also in W, so this Y is, now when we took this Y in, so when we took this Y in P of U, we get a point X in U such that P of X is in Y. Now this Y is also in W, so now it is given that this P inverse W, this is this union, this joint union of these Wi's where I is in I. So that means if this Y is in W, then its inverse image must be in some Wi. I mean its inverse image is X, so X must be in some Wi. So also since Y is in W, there exists some I in I such that P inverse of Y, which is X, this is in Wi. Now this Wi is open and U, this is open as well, and these are the open subsets of X, so their intersection is also open subset of X. Since U intersection Wi is open, so this is open, so it's open subset of X. In particular, it is open subset of Wi. Then if we take this image of this open set Wi, so this is open in Y, so then P of U intersection Wi is open subset of Y. The reason is that this P is a homeomorphism from Wi to V, so sorry W, so this is a homeomorphism. Now if we choose any subset here which is open, so indeed this U intersection Wi, this is an open subset of Wi. Now P being a homeomorphism, it carries out this open subset of Wi to an open subset of W, and hence to an open subset of Y. So this P intersection Wi is an open subset of Y. The reason being P is homeomorphism. So because P is homeomorphism, so when we restrict to P to Wi, this is a homeomorphism. Now this is the good object here, this is the good candidate here for this V. So this is the good candidate here. So take this V, so take this V to be equal the open subset U intersection Wi, it is image under P. So take this V, obviously this is an open subset of Y. So we are halfway done, because we had to prove this Y and this, we had to prove P of U is open, and for this we had to prove for each Y in P of U there exists an open subset, say V, such that Y is in V and V is contained in P of U. So this thing we have proved. Now we have to prove this Y is in V. So also this X is in U and this X is in this is an open subset of U. So one can note here that here, so we have mentioned here that this X is in Wi, so this X here, this is in Wi. Also this Y is in P of U. So if Y is in P of U, now note here Y is in P of U, so that means inverse image of Y is in U, because P is surjective. Now inverse image of P Y is nothing but X, so this X is in U. Now this X is in U and here this X is in Wi, so this X is in U intersection Wi. That means P of X must belong to P of U intersection Wi, which is, so this P of X is actually Y, and this set here is actually W here, I mean V here. So also X is in U intersection Wi, and hence this Y, which is equal to P of X, must belong to P of U intersection Wi, which is V. So we have proved this Y is in V and V is contained in Y. So this proves that this P is an open map, or P of U is open. Hence P of U is an open subset of Y. This further proves that P is an open map.